My name is Ian Johnson. I'm a graduate student at the UW. This past quarter, I've been a part of the UW's Engage program, which is an outreach event to get scientists to speak a little bit more enthusiastically about their research. I get to have this opportunity to speak to you here today because of this special bond between Town Hall and this UW program. Together they host a series called UW Science Now, which is part of the Seattle Science Lecture Series. Sponsors include Microsoft and KPLU. And now, on to our first guest. Shelley Chestler is a PhD student in the Department of Earth and Space Science at the UW. She was part of the seismology research group and is also the head of Rocking Out, the Earth and Space Science K-12 outreach program. Before coming to the UW, Shelley received a BA at Pomona College. Tonight, she will tell us about slow earthquakes, a new type of earthquake. Please help me and give a warm welcome to Shelley Chestler.
Thank you, Ian, for that introduction. Hi, I'm Shelley Chestler, and I'm a second-year grad student at the University of Washington. And tonight I'm going to talk to you about a newly discovered type of earthquake called slow earthquakes and what they can tell us about the next big earthquake off of our coast. So this is me. We're going back to January 2011. And I'm looking pretty excited right now because I'm about to get on an airplane and fly to New Zealand for a semester abroad in Christchurch. To tell you exactly where Christchurch is, if you zoom into the South Island, Christchurch is right there in the middle. So I spent 5 weeks traveling, and I was about to settle down on the second day of classes at the University of Canterbury, but I was interrupted. On February 22nd at 12:51 p.m., there was a magnitude 6.3 earthquake near Christchurch, New Zealand. To give some context, the red box is the central Christchurch, where most of the damage occurred, and I was over at the University of Canterbury, about 3 miles away. When the earthquake occurred, I was sitting at my kitchen table eating a perfectly grilled cheese sandwich. The shaking started, my roommate ran out of her room, and we jumped under the table. When we got out, nothing too bad had happened where we were. A few things had shaken off of our desks. In about 15 minutes, there was another strong bout of shaking, and we were evacuated into the courtyard. Now, our first response, I was out with a bunch of geologists. So we were like, earthquakes, these are cool. And we walked around looking for new fissures that had opened up the ground. There's a water bottle in the bottom one for scale, places where liquefied sand had bubbles up in the streets. And the extent of damage by my apartment building was just this barely visible gap right there at the top. So when it occurred, we had no idea the scope of this event. A couple hours later, we started getting news from the city center, and the first thing I remembered hearing about was this bus that had gotten crushed by a building and that people had died. And this is when it really started to hit me that I was living through this very real and serious event. And it was a very long night. What this picture is showing is people who were camping out in tents, who were displaced from their homes. They set out a bunch of these tents in a park a little bit west of the city center. I was lucky. I got to sleep in my own apartment. I actually slept on the floor of my friend's apartment because I was a little nervous. But even so, there was over 285 aftershocks above magnitude 3 that night. So those are the ones we could feel. The electricity went out immediately after the earthquake. Ours came back on the next morning, but for many people, they didn't get power for months. The pipes were broken during the earthquake, so we couldn't run water out of our faucets or drink it. We couldn't flush toilets, and the cell phone networks were overloaded because so many people were trying to call their friends and family, nobody could get through. So we were left wondering, who did we know got stuck in the city center? And actually one of my roommates went to fashion school downtown, and she turned up about 9 o'clock that night, 8 hours after the initial earthquake, after running out of her building and leaving her wallet and her cell phone behind as it collapsed around her. So this was a serious event, but we were lucky because we were far away from the city center. Just to send that message home, here's a couple buildings before the earthquake, and this is what they looked like after. And out of the 185 deaths in the Christchurch earthquake, 115 people were killed in this Canterbury television alone. After the earthquake, I got moved to Wellington because the university was closed for over a month. But I still felt very connected to this event, even though I wasn't there for this entire recovery. And it really got me thinking about what I wanted to do for the rest of my life. And I came to realize that studying earthquakes is pretty important. And I really wanted to do something that could help the community lessen the damaging effects of earthquakes. So now I'm a student at the University of Washington, and I'm interested in earthquake hazards in the Pacific Northwest. And this is what I'm going to be talking to you about for the remainder of tonight. So we're going to start back at the beginning. This is the Earth. If you cut it open, you can see there's multiple layers inside. In the very middle, there's the core, which is made of iron. Above that, there's a layer called the mantle, and the outermost shell is called the crust. Now the crust in the upper mantle is this rigid layer. So if you go and you take a rock from your backyard, that's kind of the consistency of this entire shell. Below that, there's this mushy layer. Now it's still solid, but I like to think of it being the consistency of silly putty. This outer rigid layer is divided into what we call tectonic plates. And they kind of fit together like puzzle pieces. And the boundaries between the tectonic plates are called plate boundaries. In reality, these plates don't actually look like perfect puzzle pieces. They look more like this. Some are big, some are small. And they can move around above this silly putty mushy layer below it. And when they bump into each other and run past each other, this is what causes most of the world's earthquakes. And this map shows earthquakes worldwide. Each open dot is an earthquake, and you can see they outline these plate boundaries pretty well. So I'm going to zoom in now to our own plate boundary. We have the Juan de Fuca plate trying to dive beneath the North American plate. In this sawtooth purple line we call the Cascadia subduction zone. So I'll show you a side view of what subduction looks like. And again, you can see the Juan de Fuca plate diving down beneath the North American plate. And the Juan de Fuca plate moves at about 2 to 4 centimeters per year, or as fast as your fingernails grow. So how do we get earthquakes? So the Juan de Fuca plate, again, is trying to dive beneath the North American plate, but up here we have this zone that's locked. So I want you to all put your hands together. Put one hand on top of your other hand and push really hard down and try to move your hands past each other. And you can see that it's pretty hard. Your hands don't want to move. So that's how the plates are locked. But once enough stress builds up, the plates finally slip and cause an earthquake. So what this looks like, to put it a little more simply, here's the Juan de Fuca plate on bottom and the North American plate on top. And the Juan de Fuca plate is trying to get beneath the North American plate, but it's locked and can't move. But every 300 to 500 years, you get an earthquake, and the plates slip past each other quickly and then relock. So I like to think of the Cascadia subduction zone as a sleeping beast. Right now, it's locked below us, and it doesn't seem too dangerous. It's this cute little blue dragon. But when we finally get that earthquake, it's going to be a roaring beast of an earthquake. So I want to go tell you a little more about how earthquakes happen. So the Cascadia subduction zone runs from the top of Northern California all the way up to Vancouver Island. So the earthquake isn't going to happen across that length of the fault all at once. It's going to happen in one teeny spot and then travel up the length of the fault. And this can take 2 to 5 minutes, depending if the earthquake starts at the very bottom or somewhere in the middle. So how do we record earthquakes? We use seismometers, and they're kind of like a heart monitor that measures the beating of your heart, except we measure the shaking of the ground. So when the ground shakes, we get this squiggly line recording called a seismogram. And when the ground moves up, you get an upward spike on the seismogram. And when the ground moves down, you get a downward spike on the seismogram. So this squiggly line tells us a lot of information about when and how the ground is moving. So what about the last big earthquake? So we think there was an earthquake that was around a magnitude 9, in 1700. So earthquakes are measured on a scale of 1 to 10. So magnitude 9 is huge. Again, a magnitude 3 is probably the smallest earthquake you can feel, and anything above a magnitude 8 is considered a great earthquake. So this last earthquake in 1700, it wasn't the Mushu, the dragon of earthquakes, it was the Hungarian horntail of earthquakes. It was a big deal. And it was more than 1,000 times bigger than the Nisqually earthquake, which was about a 6.7. So what about the next big earthquake? Well, what I wish I could tell you today is an earthquake this big is going to happen here at this time. But unfortunately, earthquake prediction isn't possible, and it's probably never going to be possible, so I can't tell you this. But what we do is called earthquake forecasting, and it's a lot like predicting the weather. So you open your newspaper in the morning and you see that there's a 30% chance that it's going to rain tomorrow, so you stick your raincoat in your backpack. Similarly, we can say something like, well, maybe there's a 25% chance a large earthquake is going to happen somewhere off the coast in the next 50 years. Unfortunately, preparing for a big earthquake isn't as cheap or simple as throwing a raincoat in your backpack. So it's pretty unfortunate that this type of earthquake forecasting is so vague. So the next earthquake is probably going to be sometime within the next 200 years. And we think this because the interval between these great earthquakes on the Cascadia subduction zone is around 300 to 500 years. So since the last one was in 1700, it means we're technically due. So maybe it'll happen tomorrow, maybe it'll happen 200 years from now, maybe it'll even happen 250 years from now if we're a little bit wrong about our estimation. Based on the last earthquake, we expect it to be big, which means strong shaking, but we can't tell you exactly how strong that shaking will be. We can expect the shaking to last a long time. So the shaking during the Nisqually earthquake in 2001 or the Christchurch earthquake I was in probably lasted about 15 seconds, which felt like a very long time. Now the shaking during this next big earthquake could last up to 5 minutes. And let me tell you, that's going to feel like an eternity. And we can also expect a tsunami off of our coast. But with this, that's about all we know, and it's pretty unfortunate that hazard assessment is so hard. An example of this is in Japan. So they built this 20-foot high wall off their coast to try to protect them from a tsunami. But in 2011, when they had the Tohoku earthquake, the first 30-foot wave crashed straight over that wall. So we don't want to be in a situation like that. So my question is, well, what else can give us clues about how big this next earthquake would be? And this is where my research comes back in. So here's another side view of the Cascadia subduction zone. And there's Seattle right there. And I've been talking a lot about this locked zone, this earthquake zone where you get these huge earthquakes. But below that, there's a types of earthquakes that happen every 15 months. So you're probably wondering, all right, if there's these earthquakes, they happen every 15 months, why have I never felt one of these earthquakes? And that's because they happen much slower than normal earthquakes. So remember, I said big earthquakes, they travel up the subduction zone in about 2 to 5 minutes. These slow earthquakes below them travel up the subduction zone in about 3 weeks. So they release energy much slower than these big earthquakes, and that's why they don't produce shaking that we can feel. So if we compare a regular earthquake, the Lockheed Blackbird, which is the aircraft that broke the airspeed record in the 1970s, 2,193 miles per hour, a slow earthquake would travel about as fast as a banana slug. So while big earthquakes last around 5 minutes, these slow earthquakes last about 3 weeks. Big earthquakes, they travel at 9,000 miles per hour. Slow earthquakes only travel at 0.2 miles per hour. So there's a really big difference. But if we can't feel them, how do we even know these earthquakes happen? Well, in the early 2000s, a scientist was looking at these seismograms and he noticed this weird new tectonic signal. And I'm calling it weird because it looks much different than a normal earthquake. You can see these pulses on the normal earthquake, they're much bigger, they're shorter, and this new seismic signal kind of looks like a jumbly mess of squiggly lines. So this scientist was wondering what possibly could produce this signal. Now it's important to remember that our seismometers, they can pick up anything that moves the ground. So they can pick up a train driving past, they can pick up a landslide, they can pick up really strong winds on the top of the mountain, and they can even pick up the crowds cheering and jumping for Marshawn Lynch when he makes the touchdown. But the difference, you can see these all look pretty similar to this new seismic signal I was talking about, but the difference is that they would only be picked up on a seismometer that was close to where they occurred. So for example, you'd see strong winds on a seismometer on top of Mount Rainier, and you would see a beastquake on a seismometer right across the street from CenturyLink Field. Now this new type of seismic signal was observed on seismometers scattered all around the Olympic Peninsula. And in addition, if you line them up in time, these peaks of these jumbly mess, they actually line up. So it led this scientist to realize that, hey, these were probably produced by the same thing. And it turns out this is the type of tectonic signal that is produced during a slow earthquake. And we now call this seismic signal tremor. Now these slow earthquakes are really interesting. They actually happen all over the world. They happen in Japan, they happen in the San Andreas Fault near LA, and they even happen beneath volcanoes in Hawaii. And they're really interesting because they're so different from normal earthquakes, and we want to know why. But what I'm going to talk about today, more specifically, is what these slow earthquakes can tell us about the next big earthquake. And again, that translates into the question, how strong will the shaking be in Seattle? And that's dependent on the width of this earthquake zone. So for example, if the earthquake zone is really skinny, this lower edge is going to be far away from Seattle. And you won't get as strong of shaking in Seattle than if this zone was really wide. This down dip edge, it would be much closer to Seattle and you'd get much stronger shaking. So we really want to know the width of this zone. So if we go back to our side view of the Cascadia subduction zone, again we have this big earthquake zone above. You have this zone below where we have slow earthquakes, and the thinking is that these zones meet, but they don't cross. So because slow earthquakes happen all the time, we're monitoring them and we're studying them, we're getting a pretty good idea of how wide this zone is. And from that, we can infer how wide this big earthquake zone will be, and hence how far the strongest shaking will be from Seattle. So that's good news for me. Slow earthquakes have the potential to help with hazard assessments, which makes me pretty happy because not only am I doing good science research, I actually could help the community with hazard assessment. Now to finish off tonight, I guess I'll give you a few tidbits of advice about what to do during this next earthquake. First, drop, cover, and hold, not to be confused with stop, drop, and roll. So you jump under the table, cover your neck, and grab on for dear life. You can remove high, unstable objects from your office or your bedroom. Those are things that could fall on you during the shaking. It's good to keep a pair of shoes by your bed, so when the shaking stops and things that fall on the ground, you can slip on your shoes and not cut your feet as you're leaving your house. And my favorite one is have an out-of-state contact, which was pretty important since all the cell phone networks were overloaded. So for example, maybe my mom is my out-of-state contact. Let's not assume she's sitting in the front row today. So my mom, the earthquake happens now, my mom is back in Oregon, and I get up, I'm like, okay, I'm fine. I call my mom, Mom, I'm fine. Then even though maybe my other family members can't contact me, they can call my mom and she can tell them that I was okay. So that's about all I have for you today, but I want to leave you with one more thought, that maybe you shouldn't be scared for this next earthquake, but I hope this motivates you to just be prepared, and I can take some questions.
We have an estimate of, 200 to 500 years on the distance between these giant earthquakes, how many data points do we actually have? Do we only have 2 or 3 data points? 500 years ago, 1,000 years ago, and 1,500 years ago, so we're saying it happens every 500 years. How many data points do we have of that?
So the most definite one is this 1700 earthquake, and we know pretty well when that happens. And then our other data points come from evidences of where big tsunamis have hit our coast, where you get really high sand layers. So you have many going back throughout the years, but I mean, the range is so big because it's just hard to have so many since the intervals are so long. You can only dig so deep.
I have a question. There was an earthquake up near Port Hardy, I guess Kaikut Sound, just recently, so it was around 5 something. How would that particular earthquake change? You have the spacing there, and you're showing your slide as far as the subduction zone. How does that earthquake relieve stress and affect the probability of a larger one? And a second question regarding the slow earthquake zone and the fast earthquake zone. If you make the slow earthquake zone larger and further away from Seattle, doesn't that relieve the stress down in the lower levels, and doesn't that make a narrower area between the stresses for the major earthquake and the slower ones, and increase the probability of a larger one?
Okay, so your first question was about the recent earthquake in Port Hardy, and I mean, I just actually looked at that yesterday, and it was on a different kind of fault than, it was on a type of fault that moves past each other instead of diving under each other. So I'm not quite sure how that exactly would push stress onto the subduction zone, but I don't think it would have that big of an effect.
Or relieve it, yeah.
Yeah, and as far as so you have this slow earthquake zone below, and actually when slow earthquake's happening, they're relieving stress down in that zone, but the stress could be moving up into the big earthquake zone. So it's not kind of changing the width of this zone, it's just loading that zone. And it's actually maybe a higher probability that a big earthquake could happen during a slow earthquake. But there hasn't been enough case studies of a slow earthquake leading to a big earthquake, since we only discovered slow earthquakes about 20 years ago for us to say that definitively.
20 years of data, but it does seem if you make that area smaller, it could mean higher stresses over that. So that sounds like what you're saying. Thank you.
I just wondered if you could give us a little bit more information on what types of data indicate slow earthquakes that you use in your research.
So I'm a seismologist, so I usually only use this tremor data, so when this wiggly tremor is happening, but you can also use GPS data to know when they're happening. So normally when the plates are moving this way, it's diving down and it's pushing the land really slowly to the east. And during these slow earthquakes, these GPS stations right above the slow earthquake zone actually slightly move back to the west. So you can see every time a slow earthquake is happening with GPS data.
If it's been 15 or 20 years since we've known about these, why isn't there massive statistical gathering happening? Why aren't we coordinating across the world, saying we had a big earthquake? Was there 5 slow earthquakes the year before the big earthquake?
Well, I mean, there's a lot of slow earthquakes. They're happening all the time here and in Japan, but there just hasn't been very many big earthquakes. And probably the best example is the Tohoku earthquake in 2011, and then there was recently some in Chile. But it's just, 3 or 4 big earthquakes in this 20-year time isn't enough data points really to make a firm correlation. We need more big earthquakes to actually know how slow earthquakes are affecting these big earthquakes for sure.
Have you tried correlating the slow earthquakes versus geomagnetic data, for example, solar proton fluxes, A indexes, and all of that stuff? I was just thinking of that would be a possibility. You know, you're looking at the heat generated in the planet and all of that, you know, those very large-scale planetary indices.
I don't know. I haven't tried to do that. I haven't heard of that. Sorry.
Thanks.
I've heard about something called a Seattle fault. It's like somewhere around Seattle. Is that true? Could that fault slip and could it cause a tsunami in Seattle? And how big would the tsunami be? Do you know?
Thank you, roommate. Yes, there is a fault that runs beneath Seattle, and it doesn't generate as big of earthquakes as the big fault, the Cascadia subduction zone off our coast, but it is thought that if the earthquake is big enough, probably above a magnitude 7, it would generate a tsunami in the Puget Sound.
Does a seismometer only record tremors from a subduction zone earthquake? Or I was just curious about where there's two plates shearing against each other. Does it also read that, or is it different?
Yeah. So the San Andreas Fault near LA is a fault that's moving past each other, and it actually records tremors deep in that fault as well.
Can I ask a question without going up to the microphone?
Shelley will just repeat it.
Okay. So I moved recently from Oakland, California, a mile from the Hayward Fault, and the Bay Area actually has really nice maps of the geology of the area, because my understanding is that the shaking that you experience is a function of not only the magnitude but the geology under your feet, right? And so is there a resource like online or something that would have that information like within some reasonable distance, so you could look at different neighborhoods, for example, and be like, yeah, the shaking was likely to be worse here or better here?
Yeah, on the USGS webpage, you can pull up shake maps for all of the Seattle areas and possible liquefaction maps as well.